Hi students, we're going to start class 10 CBSE exercise 1.1 and the question number 1. Let us start question number 1. This says use Euclid's division algorithm to find HCF of 135 and 225. It is very easy. All you need to know is to find out what is all about Euclid's division algorithm that says whenever we have a division, as you know, the division is like this. Dividend is equal to divisor multiplied with the quotient, then add the remainder. This is exactly what Euclid's division algorithm all about. Now, to solve this, you need to know which is the bigger number and the smaller number. Here, 135 is smaller number and 225 is bigger number. What we do now, we divide 225 by 135. We write here 135 divides 225. It goes one time, 135 ones are 135. You get 90 as a reminder. Applying the Euclid's division, which says A is equal to BQ plus R, where A is dividend, B is the divisor, Q is the quotient, and R is the remainder. Now apply this, whatever we got in the first step. 225 is the dividend, 225 is equal to B. Divisor here is 135 is the divisor and this is the dividend. Multiply with the quotient. This is the quotient. Into 1, add the remainder. In this case, remainder is 90. To get the HCF of any two numbers, you need to go until you get remainder 0. Next step is we make this divisor as the dividend and we divide this 135 by 90, which was remainder in the first case. Now this goes one time and the remainder is 5. 13 minus 9 is 4. Now in the second step we write in the Euclid's division algorithm method. Here 135 is the dividend, which is equal to the divisor. This is 90 into quotient. Quotient is 1. Add that to the remainder, which is 45. We still have not got 0, so we are yet to get HCF, which is our answer. What we do in the third step, we take this divisor as the dividend. Divide that by the 45 remainder. We know it goes 2 times. 45 into 2 is 90 and you get 0 as a reminder. Yes, we came to 0 as a reminder. Here we apply the same algorithm, which is 90. 90, as you know, in this case, third case, 90 is dividend and the divisor is 45 multiplied by 2, add 0. These are the steps you have to know to write down to prove that you are going to get HCF by this Euclid's division algorithm. As you got 45 as HCF, this is HCF because the remainder is 0. You have to do this step by step till you get 0. The answer is HCF of 135 and 225 is equal to 45. This is the answer. Now we will go to the second question of the same question number 1. Find out HCF of 196, question number 1, and second in that is find the HCF of 196 and 38220. Two big numbers here. As you know, algorithm method says A is equal to BQ plus R. A is the dividend, Q is the quotient, B is the divisor, R is the remainder. To start with, we have to know which is the smaller number. As you know, 196 is smaller than 38220. So now let us start finding out HCF by division method. What we do here, we divide 38220 by 196. Let us start doing it. 196 ones are 196. 12 minus 6 is 6. 7 minus 9 is 8. We get 2 here. 2 minus 1 is 1. Now bring this 2 down to 186. So it will be 1862. Now it goes 9 times, which is 4, 6, 7, and 1. The balance is 12 minus 4 is 8. And 15 minus 9 is 9. Bring this 0. This becomes 980. It can go 5 times. 980. The remainder is 0. In the first case itself we got the remainder 0. Therefore, the HF is of 196 and 38220 is equal to, this is the HF. 196 is the HF of these two numbers. We could get this in the first step itself. So we are going to solve the third part of the first question, finding out HCF of 867 and 255. As you know, the Euclid's division lemma says dividend is equal to divisor into quotient plus R. We write this in this form also. A is equal to BQ plus R, where A is dividend and B is divisor. Now, when we start doing finding out HCF of 867 and 255, all you need to know is which is greater number and which is smaller number. 255 is smaller than 867. Therefore, what we do, we divide 867 by 255. And this goes 3 times. You get 5, 6 and 7, 765. The answer is 102. The remainder is 102. Hence, you are yet to arrive at the answer to find out the HCF of these two numbers. Now we write this first step, substituting the values here. Here is 867, which is dividend. This is the dividend, and is equal to B. B is the divisor, and this is the divisor. 255 is the divisor. And into quotient. Quotient is 3. Add the remainder at the last. 867 is equal to 255 into quotient. Quotient is 3 plus 102. When you simplify this, you get 867. Well, we go to the next step of the question. 255, which is divisor, becomes dividend here. and we divide this by 102, and this is about 2 times, you get 204. The remainder is 51. We are yet to get the answer, and we substitute this value here in the second step. 255 is the dividend. This is the dividend, which is equal to divisor 102 into quotient 2 plus the remainder 51. The next step is this 102 becomes dividend here. 51 divides this. When we do this, you get exactly 2 times. 102 times 102 is the answer after multiplication, and the remainder is 0. When you arrive at the 0 as the remainder, we have come to the end of the calculation. And this again we substitute here. We write down here 102, which is dividend, will be equal to 51 into 2 plus remainder 0. Now you need to write all this. This is called working. After writing this, you will arrive at the answer. The answer is, as we said earlier, the divisor in the last step, which is 51 here, becomes the answer. Therefore, HCF of 867 and 255 is equal to 51. This is the answer. Students, now you see question number 2 says this. Show that any positive integer is of the form 6q plus 1, 6q plus 3, 6q plus 5, where q is some integer. It can be any number. We start now. As you know, Euclid's division algorithm says a is equal to bq plus r. A is the dividend, b is the divisor, q is the quotient, and r is the remainder. Here are where r is greater than 0 or equal to 0. That's the condition. Remainder will never be less than 0. It is always greater than 0, or it can be equal to 0. And this also be noted that it is less than b. Less than b. What is b? Yes, it is the divisor. Now, what are the possible numbers of r? Possible numbers. Possible numbers of r is equal to, as you know, we said it is equal to or greater than 0. So it can be 0, it can be 1, it can be 2, it can be 3, it can be 4, and it can be 5. Not beyond this, because as you know, the logarithm says it should be less than b. In this case, b is 6. Let us write down that also. b is 6. This you should know. In the question, it is written 6. Therefore, b is 6. And r can never be 6 or more than 6. It is less than 6. So, these are the possible numbers of r. 0, 1, 2, 3, 4, 5. Now, apply one by one and find out which is odd number. Example, a is equal to 6q plus r. So we take when r is equal to 0. We will take the first case. Applying r as 0, you get this equation. In this case, r is equal to, a is equal to 6q. And we know that in the table of 6, you always get even numbers. Example, 6 ones are, 6 twos are, 6 threes are, 6 fours are. Likewise, you get all even numbers. Now, plus 0 does not change the status of even or odd numbers. 6 remains 6. It is even number. When you add 0, 12 remains as 12, which is again even number. When you add 0 to 18, 18 is again even number. 24 is again even number. So by adding 0, which is the first value of r, all these numbers will remain as even numbers. Let us write down this. In the next case where when the r value is 1, we take this as r value. Now apply a is equal to 6q plus 1. When you do this, imagine you put 6 plus 1, it becomes 7, which is odd number. When you add 12 plus 1, 13 is an odd number. When you add 1 to 18, becomes 19. That is again odd number. So whenever we add r, which is 1 here, to 6q, you get odd numbers. Please note that in the first case it is even. In the second case, when the value of r is taken as 1, you get only odd numbers here. A becomes odd number. So let us go for the third case when r is equal to 2. Yes. A is equal to 6q plus 2. Adding 2 to 6, you get 8, which is even number. When you add 2 to 12, that becomes 14, which is even number. When you add 2 to 18, it becomes 20, which is even number, likewise. So by adding 2, you get only even numbers. The A becomes even equation. Let us take when r is equal to 3. This is this case. A is equal to 6q plus 3. It is very clear. By adding 3, you get 9, which is odd number. Adding 3, 15, you get odd number. 18 plus 3, 21 is odd number. 24 plus 3, 27 is odd number. So it's very obvious that you get odd numbers here. When we go for the fourth, taking odd value as fourth, when r is equal to 4, you can understand 6 plus 4 is 10, even number. 12 plus 4 is 16, even number. 18 plus 6, 24, even number. So you get all even numbers. Finally, when odd is taken as 5, which is this, 6q plus 5. 6 plus 5 is 11, you get odd number. 12 plus 5, 17, odd number. 18 plus 7, 25, odd numbers. So you get only odd numbers. You can find out this is one case where you get odd number. This is second case where you get odd number. The third case where you get odd numbers. So you can find out what you find here. Therefore, we find any odd integer is in the form of 6q plus 1, that is this, 6q plus 3, which is this, odd, or 6q plus 5, which is this. We have given the answer. I read out the question. An army contingent of 616 members is to march behind an army band of 32 members in a parade. The two groups are to march in the same number of columns. What is the maximum number of columns in which they can march? The question looks bigger and tough, confusing. Students, I tell you, it is the easiest question. You can solve in just one step. All they want you to find out is HCF of two numbers, 616 and 32. That's all. But they want to confuse you. Don't worry. Let us understand the question. Question says, there is a band of 32 members. In a parade, in an army parade, you can find some people in the band. They march in the front, and the rest of the parade contingents they move in the at the back, and they follow those band steps. Here the band members 32, and here the contingent members 616. They must march in same number of columns. In the sense, what is a column? The one which goes from top to bottom. These are all the columns. And when it goes from left to right, they are the rows. These are rows, these are columns. Suppose if 32 members are said to go in some columns, say about 8 people or 4 people, they go, and behind them 616 people should also march in the same way in the same columns. So you need to find out how many of people in each column can march, behind which these members also will march. The question looks a little tough, but the question is simple in fact. You need to find out the HCF. Whatever is the HCF of these two numbers will be the answer for this question. Here you need to find out HCF of 616 and 32. That's all. As you know, 32 is smaller than 616. Therefore, we are going to divide 616 by 32. Again, applying Euclid's method, you will write down this: A is equal to BQ plus R, where A is the dividend, B is the divisor, Q is a quotient, R is the remainder. This must hold good whenever we talk about Euclid's division method algorithm. Now, knowing this, 32 is a smaller number, we divide that 616 by 32, and this goes one time. The remainder is 29. Take this 6 down, you get 9 times. The answer is 288, and you have the balance 8. We did not get 0, therefore we are yet to continue to get HCF. In the first case, we write down, in the place of A, we write down 616 is equal to 32, which is B divisor, multiplied by quotient. This is a quotient, 19 plus R. This is R, remainder 8. What we do? We take 32 as a dividend here and 8 as the divisor. As you know, it goes 4 times. 8 for the 32, you get 0 as the remainder. We got 0 as a remainder. Therefore, we have come to the end of the calculation. We write that here 32 is equal to 8 into 4, divisor into quotient, plus R. R is 0. These are the steps we have to write down to show the correct answer. And the HCF is, as I said, whichever is the divisor in the last step where you get 0 as a remainder, that divisor is the HCF of those two numbers. Therefore, HCF of 616 and 32 is equal to 8. But what is the answer? Answer is, what is the maximum number of columns in which they can march? The answer is 8 is the number of columns they can march. We write down that the number of maximum columns they can march is 8. Now, let us start about Fourth question, which says use Euclid's division lemma to show the square of any positive integer is either of the form 3m or 3m plus 1 for some integer m. See, Euclid's division lemma says a is equal to bq plus r. We must know r, which is remainder, will never be more than 0. Therefore, will never be less than 0. It can be either more or it can be 0. And it should always be less than b divisor. This is the condition. Remainder is either equal to 0 or more than 0 and should always be less than divisor. This is the condition. This is Euclid's division lemma's condition. Now, let us start, and we know the value of b here in this question, which is 3. So for the calculation, we use b as 3, and we'll start now answering. So what we do now, let us take a. Let a be any positive integer. Now, we also should know what all the possible values of r. When we have 3 as b, possible values of r is equal to 0, 1 and 2. We should always remember when b is 3, r value should be 1 and 2 only. When it is 4, it becomes 1, 2, 3. So it should be always less than this number. So the possible values of r will be 0, 1 and 2. We are going to substitute this value in this so that we arrive at the answer. To start with, we take r as 0, right? And take this a plus bq, a is equal to bq plus r. Now put 0 here, it becomes a equals aq, bq. Now value of b is 3, therefore a will be equal to 3q. This is number 1. What you have to do now, you have to square both sides. Square both sides. We must remember that in mathematics, LHS will be equal to RHS. When you square one side, you have to square the other side to make sure that the value does not change. Similarly here, once a square will be equal to 3q whole square. We have squared both LHS and RHS. A square is equal to 3q whole square. When we open this becomes a square equals 9q square. To get our answer 3m, what we do, we break this into 3 into 3 like this. The value does not change. 3 into 3 is 9, q square is there. All we have done is taken out 3 separately and 3q square becomes some integer. So what we do, we put let m be equal to 3q square. This is already written in the question itself, some integer m. So this is some integer. Therefore, this you can treat as m. A square is equal to 3m. This is one observation. The second observation is when the r value is taken as 1. It is this. R value is taken as 1 or is equal to 1. Put this value in our equation bq plus r. A is equal to b is 3, q is written as it is, and this is 1. Now you have to square both sides. Square both sides. Then this becomes a square 3 cube plus 1 whole square. Please remember, put the brackets for the 4 RHS and then square it. Now this follows the identity a plus b whole square, which is equal to a square plus b square plus 2ab. Use this identity to solve this. This becomes 9q square plus 1 square is 1 plus 2 into 3q into 1, which is 9q square plus 1 plus 3 into 2 is 6q. Now put this 9q square and 6q together plus 1 at the last. Now a square is equal to, take 3 out, 3q square plus 2q plus 1. Please remember, this is some integer which is represented by letter m. After this, a square becomes 3m plus 1 because, as I say, whatever is written in the bracket is some integer which we want to represent by the letter m, which is already written in the question itself, some integer m. So this is some integer, and this you can write as m. We finally arrive at a square, which is equal to 3m plus 1. This is case 2. Okay, students, we are going to talk about question number 5. This says, use Euclid's division lemma to show that the cube of any positive integer is in the form of 9m, 9m plus 1, or 9m plus 8. For this, let us first write down Euclid's division lemma, which is A equals BQ plus R, where R is more than 0 or equal to 0, and it should always be less than B. This is the condition. As I said, Euclid's division lemma or algorithm, this is the condition. You need to know this. Now the value of B is taken as 3. We will write down all possible values of remainder R. Possible values of R is equal to, as we know, it is either equal or more. So one possible value of R is 0 and 1 and 2 only, because our value should never be more than or equal to B. Therefore, we can take 0, 1 and 2 as the possible values of R. R is remainder. Now we will take one by one value of R. Let us start 0. When R is equal to 0, what happens to this? A will be equal to BQ plus R. We will put the value of 0 here, R. A will be equal to, B is 3. We write Q as it is, plus R is 0. This is the first case. Therefore, A is equal to 3Q. Now we have to cube both sides. Both sides means LHS and RHS. When you cube this, this becomes A cube and this becomes 3Q cube, whole cube. Will be equal to A cube, 3 3 is a 9, 9 3 is a 27, Q whole cube. This will be the first case. Here we can do one thing, we can go further. A cube is equal to, we take out 9 and then put 3Q cube separately, so that we will be able to find the answer easily. because here we have to see 9m. Here 3q cube is some integer which you can represent by the letter m. Therefore, this becomes a cube 9m. This is case 1. Now we will take the value of r as 1, right? Okay, when r is equal to 1, what happens to our Euclid's division lemma, which says a is equal to bq plus r. A will be equal to 3 because b is 3 here, q as it is, and r value we have taken 1. So we put 1 here. Now again, cube both sides. Cube both sides. Both sides means LHS and RHS. Then becomes a cube which is equal to 3q plus 1 whole cube. I was telling you there is an identity which we have to use it here. The identity is a plus b whole cube, which says a cube plus b cube plus 3 into a into b into a plus b. A plus b whole cube is equal to a cube plus b cube plus 3ab into a plus b. This is the identity which we have to use it here. Now let us open this. 3q whole cube plus 1 cube plus 3 into a into b. This is a, this is b. 3 into 3q plus 1. Then open the bracket. A plus b. This is a and this is b. Right? Now we will simplify further. This becomes 27q cube plus 1 cube is again 1 plus 3 3 is a 9 q plus this is 3q plus 1. We write this as it is. Now further we go 27q cube plus 1 plus 9 3 is a 27 q square. We have two q's here. Q into q is q square plus 9q into 1 is 9q. Now further, we keep all the 27q cube, 27q square and 9q together. This is how we write. And put 1 in the last. What we do now, we take out 9 as a common factor. 9 3s are cube plus 9 3s are q square plus q plus 1 as it is. Now this will be equal to, we are talking about a cube, 9 into m plus 1. I will tell you how. This, the whole thing, whatever you see in the bracket is some integer which we want to represent by the letter m. Therefore, a cube becomes 9m plus 1. This is case 2. Value of r as 2. Writing a equals bq plus r. A is equal to 3q plus 2. Now cube both sides. A cube will be equal to 3q plus 2 whole cube. Again, Using the identity a plus b whole cube, you know it is 3q whole cube plus 2q plus 3 into 3q into 2, 3q plus 2. This follows a plus b whole cube, a cube plus b cube plus 3ab into a plus b. When you simplify, you get 27q cube plus 2 to the 4, 4 to the 8 plus 3 to the 9, 9 into 2 is 18, q. 3q plus 2 is written as it is. Again further, 27q cube plus 8 plus 18 into 3 is 54 q square plus 8 into the 36 q. Here what we do, we take out 9 as common factor, will be 3q whole cube plus, for 54 we take out 9, 9 6 the 54 q square plus 9 4 the 4 q. Put this 8 to the last. Whatever is written in the bracket, all this will be some integer which is equal to m as per the question. Therefore, a cube is equal to 9 into m plus 8. This is our third observation. The answer is, we can write down by observation 1, 2 and 3. We find the cube of any positive integer is in the form of 9m plus 1 or 9m plus 8. We have arrived the answer. Okay students, we have completed the exercise 1.1 completely. Hope you understood the questions and answers, how to answer them. If you have anything to write, please write in the comment box. Thank you.